Integrals play a major role in the fields of fluid mechanics, probability, and statistics. Hi, my name is Tom Atwater, and in this lesson we will apply the concept of the integral to many different real-world applications. Let's dive right in with the different ways that the definite integral can be used. A leaky bucket is lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 Newton meters. The bucket starts with 490 newtons, approximately 50 liters, of water, but it leaks at a constant rate and just finishes draining as the bucket reaches the top. How much work was done lifting the water to a point 20 meters above the ground? Do not include the rope and the bucket. Okay, so what we need to do here is set up an equation where we know that the force is equal to the weight of the water, but stuff is leaking out. So what we have is that the force will be equal to the weight of the water, 490, but then we have to take into account that at a height of x, we would have the ratio of water as 20 minus x divided by 20, so that when x reaches 20 meters high, of course, there would be no water left. And at the beginning, when we have the bucket on the ground, so x would be 0, we would have the full 490. So that's the expression. Let's simplify that a little bit. That would equal 490 minus 24.5x. And so that would be the force of lifting the water. Now, in order to do the work, remember, is the integral of the force. So in our particular example, we would have the integral from 0 to 20 of 490 minus 24.5x dx. And so we would have that the work would equal 490x minus 12.25x squared, and that's evaluated from 0 to 20. And when we plug that in, we will find the answer to be 4,900 joules of work. All right, so that was a very quick and basic example to remind us of that work is the integral of the force applied. Let's do another example. Let's take a conical tank, which I will show you in a figure, and it's filled to within 2 feet of the top with olive oil, which weighs 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? So let's take a look at the picture. Here we have our conical tank, and we have it partly filled with oil, the olive oil. It's 2 meters shy of the top. And some of the other information that we need to look at. Well, what we're going to do is look at, of course, these little cylindrical discs, which have a height of dy and a radius of 1/2 y. And we're going to take and integrate those over the entire height of the cone that we're interested in, and that height 10 minus y, because we are pumping the oil up to the rim of this particular cone. The limits of our integration, of course, are from 0 up to 8, since we know that the height is 2 feet below the rim, and of course, that total height is 10. So now, let's set up our integral that we would use with that information. So, what we would have is that this would be the integral from 0 to 8 of, what we need is the force, and the force is, the weight of olive oil is 57. Then we're going to multiply that times the disk, which is pi, r squared, which would be equal to 1/2 y squared, and that would be then multiplied times the height, which is 10 minus y, and then that is all with respect to y. So our integral becomes, from 0 to 8, 57 pi over 4, and I'm getting the 4 from this 1/2 squared, and then it would be y squared times 10 minus y dy. And take that one step further and integrate it. We would have 57 pi over 4, which I'm taking outside, and then we would have 10 y cubed over 3 minus y to the 4th over 4, evaluated from 0 to 8. So plugging that into our calculator to do the arithmetic, we would find that this is equal to 30,561 foot-pounds. All right, great. So here's another example of where we can use the integral of the force to find the work. And again, we use the concept of dividing it up into little circular discs, where here's our area, there was our height, and then including that 57, which is the weight of the olive oil. All right, great. Now, let's turn our attention to fluid force and fluid pressure. The fluid pressure, P, which is the force per unit area at a depth h, is P equals WH, where W is the weight density, weight per unit volume, of the liquid. So let's take a look at an example where we can apply this formula and the use of integrals. Let's say that we have a rectangular freshwater tank, and it has a base of 2 feet by 4 feet and a height of 2 feet, and those are the interior dimensions. And it's filled with water to within 2 inches of the top. Find the fluid force against each end of the tank. Then, suppose the tank is sealed and stood on end without spilling any water, so that one of the square ends is the base. What does that do to the fluid forces on the rectangular sides? Okay, so this will give us an opportunity to use that formula and apply integrals to finding the solution to these questions. So let's set up our integrals. In order to do that, we need to know our limits of integration, remembering that the water level is 2 inches short of the top and that the entire height is 2 feet or 24 inches. That means it goes up to 22 inches. And in terms of putting that back into feet, it would be 22/12 of a foot. In addition, the other piece of information you need to know is that the weight density for water is 62.4. So now we can set up our integral. We would have the integral from 0 to 22/12 feet, and the weight density of water is 62.4, and we want the end of the rectangular fish tank, and so that area would be y times 2 for 2 feet, and y, of course, is our height. 2 feet is the width of the end area, times dy. And so what we get when we integrate this is that we have 62.4 y squared evaluated from 0 to 22 twelfths. And when we plug that in and work it out, we get an answer of 209 and 73 hundredths. And that would be pounds. So that's our part A. Now, for part B, we take the tank and we stand it on its end. No volume of water is lost, so you would have to do the calculation, which I've done, that tells us now that the height of the water is going to be 4 inches short of the top of the tank. And because we've turned the tank so it's now tall, it's 4 feet or 48 inches, which means that we're doing it up, the limits for our integration go from 0 up to 44 twelfths of a foot. So that's our new limits of integration, 0 to 44 twelfths of the foot. In terms of we still need our 62.4, and our height would still be considered y, and we're still looking at the width of the tank remaining at 2. So we actually have the same integrand inside, so we know that that will be 62.4 y squared evaluated from 0 to 44 twelfths. And as you would expect, this time our answer is larger. We have 838 and 93 hundredths pounds. And that's the answer we would get when we flip the tank so that it is standing on one of its ends. All right, well, now it's time to look at probability. Let's take a look at the definition of probability. A probability density function is a function f of x with domain all reals such that f of x is greater than or equal to 0 for all x, and the integral from negative infinity to infinity of f of x dx is equal to 1. Then the probability associated with an interval, closed interval a to b, is the integral of f of x dx from a to b. Let's take and apply this formula to an example. We have to find the probability that a clock stops between the hours of 1 o'clock and 5 o'clock. First, we have to set up what the probability density function looks like. And what it looks like is this. F of t would be equal to, and it comes in 2 parts. We know that it's going to be equal to 1/12 when t is between 0 and 12. And that f of t is going to be equal to 0 otherwise. And our integral that we're interested in is the integral from 1 to 5 of f of t dt. Well, in this particular case, we know that we have 4 intervals, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. So therefore, this is going to be 4 over 12, or 1/3. So that the chances, or the probability, that a clock stops between the hours of 1 and 5 is 1/3. So let's take a look now at what's called the normal probability density function. The normal probability density function, the Gaussian curve, for a population with mean of mu and standard deviation sigma is given by the formula f of x is equal to 1 over sigma times the square root of 2 pi times e raised to the power negative quantity x minus mu squared divided by 2 times sigma squared. Well, that's a very ominous looking formula, and let's talk a little bit about what this normal probability density function is. The normal curve is often called the bell-shaped curve, and it's one of the most significant curves in applied mathematics because it enables us to describe entire populations based on statistical measurements taken from a reasonably sized sample. The measurements needed are the mean, which is abbreviated with the Greek letter mu, and the standard deviation, which is abbreviated with the Greek letter sigma, which your calculators will approximate for you from the data that you enter. The symbols on the calculator will probably be x bar and s because they do not have those Greek letters labeled on there. Once you have the numbers, you can find the curve by using that formula, which was discovered by Carl Friedrich Gauss. Let me show you now the curve itself. And this is the normal bell-shaped curve. And what I have is an example of the interval from A to B, similar to what we just did with the clock. This could be our interval starting at 1 and going to 5. What we say is that when we integrate it, remember the integral is the area under the curve. So this shaded region is the area under the normal distribution curve for the interval from A to B. Now, the mean, mu, represents the average value of the variable x. The standard deviation measures what we call the spread, or what might be the scatter, around the mean. For a normal curve, the mean and standard deviation tell you where most of the probability lies. Let's take a look at that. We have what's called the 68, 95, 99.7 rule for a normal curve. And what it tells us is this: 68% of the area will lie within 1 standard deviation of the mean. That is 1 standard deviation below to 1 standard deviation above. And that 95% will be within 2 standard deviations, while 99.7% will lie within 3 standard deviations of the mean. Here's a graph to show you that. This particular graph has a mean of 0. And so it's easy for us to see that if we go 1 standard deviation above and 1 standard deviation below, that we would have 68% of the area. And as we've already said, 2 standard deviations above and below give us 95% of the area, and that 99.7% of the area is 3 standard deviations. There are many different sizes for the bell-shaped curve, and depending on the value of the standard deviation, you get a different shape. So we can see here that with a standard deviation of 1, we have the red curve. And comparing that then to a standard deviation which is larger, in other words, a standard deviation of 2, that spreads the curve out more. While if we decrease the standard deviation, for example, a standard deviation of 1/2, you can see that what happens is we decrease the spread, narrowing the shape of our bell-shaped curve. Okay, well, let's take a look at an example where we can apply what we've been learning. Suppose a telephone helpline takes a mean of 2 minutes to answer calls. If the standard deviation is sigma equals 2, what percentage of the calls are answered in the range of 0 to 4 minutes? Well, let's take a quick look at that. We know that the mean is 2. We know that the standard deviation, sigma, is equal to 2. So if we go up 2 units, that brings us to 4. If we go down 2 units, that brings us to 0. I'm sorry, go down 2 units, which is 1 standard deviation. So that's our interval that we're interested in, right? From 0 to 4. And that interval is 1 standard deviation below and above the mean, which means that 68% of the data lie within that interval that is between 0 and 4 minutes for the length of the wait to answer the phone call. All right, let's take a look at another example. Suppose that we have frozen spinach boxes that are marked as 10 ounces of spinach, and they have a mean weight of 10.3 ounces and a standard deviation of 0.2 of an ounce. What percentage of all such spinach boxes can be expected to weigh between 10 and 11 ounces? What percentage would be expected to weigh less than 10 ounces? And what is the probability that you will actually get one that weighs exactly 10 ounces? Okay, well, what we need to do is plug in the given information of our mean weight of 10.3, our standard deviation of 0.2, into our formula that we looked at earlier. So here it is. We've plugged in our standard deviation, 0.2, and we've plugged in our mean average weight, 10.3 ounces. And what I recommend that you do is you enter this into your calculator as y sub 1. In other words, enter it into the equations button and enter this formula into y sub 1. Because now, in order to do part A, we can use n int of y sub 1, comma, x is our variable, comma, and we were interested in the interval from 10 to 11. And when you do that and hit the enter on the calculator, you'll find this to equal 93.3%. So that's telling us that we would expect 93 and 0.3% of all these spinach boxes to be between 10 and 11 ounces. What about part B? Let's take a look at that. We're going to use n int again, and this time we're using the same exact formula, and we use x as our variable, but our interval this time is going to be 9 to 10. Now, you may ask, well, how did I come up with that 9 since all it said was we wanted the boxes to be less than 10 inches? Well, the way that I came up with that is if you look at the function itself, the graph of that function, what you'll find is it is the normal bell-shaped curve. But as soon as you get down to 9, that the curve is so close to the x-axis, it's so close that essentially when we say we want them to be less than 10 ounces, it's equivalent to saying between 9 and 10 ounces. So that's where I got the 9 was from examining that graph and seeing that that's the end point that I could use for my interval. Well, when we plug this in and hit our enter, we will find that this is equal to 6.7%. All right, so now we need to do part C. Part C, it's interesting because, of course, if this is a continuous distribution, which it is, then the integral from 10 to 10 remember, when we do integrals and they have the same limits of integration, 10 to 10, it would yield 0. So that is the answer. The answer is 0. However, if we wanted to come up with some idea, we could do an integration from 9.95, so 9 and 95/100ths, and up to, let's say, 10 and 5/100ths. And we could plug that in, and we could come up with a number of boxes that would weigh, well, rounding off to 10 ounces. However, as I said, for a continuous distribution, the answer really is 0. So it's time for you to try a problem. And the problem that I would like you to do is this. The mean height of the adult female in New York City is estimated to be 63 4/10 inches with a standard deviation of 3 2/10 inches. What proportion of the adult females in New York City are A, less than 63 4/10 inches tall, B, between 63 and 65 inches tall, C, taller than 6 feet, and D, exactly 5 feet tall. All right, pause the video while you work on this problem, and when you are finished, restart the video to check your solution. So to do this problem, we need to plug our values of the mean and the standard deviation into our probability density function formula. So let's take a look at what that is. We would have f of x is equal to, here's my standard deviation, and there's my mean plugged in. Once again, I will recommend, in fact, I will insist that you use your calculator and enter this formula into your y sub 1 equation. Because then, in order to do this problem, we can use the n-int. Now, for part A, we don't need to use n-int because they asked us how many females would be less than 63 4/10 inches. But that is the mean, which means we know that 50% are less than that and 50% would be taller than that. So 50% is our answer to part A. What about part B? For part B, we would do n-int of y sub 1, comma, x, comma, and our interval was 63 to 65 inches. And when we plug that in, hit our enter key, we'll find that it's 24%. So 24% of the adult females would be between 63 and 65 inches tall. Part C, we'll use n-int again, so that it would be n-int of y sub 1, comma, x, and this time we are going from 72 inches up to 80 inches. And of course, you'd expect that with a larger interval than what we had before, we should expect a larger percent, and in fact, we get 36%. And then finally, for part D. Part D, well, again, if we assume that it's a continuous distribution, then your answer is 0 because we're going to integrate with the limits of the integral being exactly the same. And so therefore, it is 0. However, you could use the n-int function and plug in like 59.5 to maybe 60.5 inches. And if you were to do that using 59.5 and 60.5, you'd come out with approximately 6.7%, or no, I'm sorry, 7.1%. 7.1% would be exactly that tall. But again, the true answer is 0. All right, great work today. Now in this section, we looked at applications of the integral to both science and statistics. We had some good formulas for you to look at for probability, and Be sure to work those exercises that your teacher assigns, and we'll see you next time.